Okay, so first, homework 5 will be out today. And given that you have Thanksgiving break, it will only cover lectures 15, 16, 17. So you can get started today itself. And I'll have office hours today and on Wednesday to help you with that. And if you have any questions, you can also ask on next time and then I'll answer them as soon as possible. Okay. And exam 2 solutions are up. Grading is going to take some time. Even scanning is going to take some time. Earlier we had, yeah, it will be at least next week. We'll try to do it over the break. All right. Any questions about the exam or the homework? Okay. So last class, we talked about context-free grammars, kind of defined what they were. We saw some examples. We had some heuristics, kind of, for designing context-free grammars, we had some fun playing with them. And what we do today is kind of start asking our usual sort of meta questions about context-free grammars, right? We have a new sort of class of functions. Are they computable? If I give you a grammar as input, what can you tell me about it? What kinds of questions can you answer about them? And can they compute everything? Are they as powerful as Turing machines? We already know that they're more powerful than DFAs, but let's see how they compare to other models. Okay. So the starting question today is going to be the following, right? So let's think of kind of perhaps the most basic algorithmic question that you can think of when it comes to context-free grammars. And any guesses what it might be? Yeah, I show you a grammar, right? Suppose, I give you a grammar. Okay, so I give you a grammar, like, I tell you what are the variables, what are the rules, what are the terminals. And so the grammar is V sigma, the rules and the starting symbol, right? You can imagine I tell you the grammar for, maybe something quite complicated like Python language, okay? Or even maybe something simple, whatever it is, right? And then I also give you a string from the terminals, okay? And I ask you, does X match G? Okay, can one generate the string X from the grammar, okay? Or is X in the language generated by the grammar? All equivalent ways of asking, right? What is the value of the function defined by the grammar at the string? Okay. So I give you the grammar for maybe Python, and then I give you a Python program, or something supposedly a program, and you have to tell me, does it at least syntactically belong to this language? Okay. So how would we answer such a question? Again, we're thinking of an algorithm. We can think of high-level programming, anything else, anything that seems natural enough, but we want some kind of computational procedure to decide this. So let's, take some dummy example. So let's say my grammar is something like this. S is the start symbol, and then you have maybe this. It's some weird grammar, and I give you a string X here. So how would you check if I can derive the string X from this grammar? Any suggestions? Like for DFAs, if I give you the DFA and the string X, then you can just run the DFA on the string and be done with it, right? But for grammars, it's less clear what to do. What would be the starting point? Well, ideally, what would we like to do? Can I match kind of, pieces of X one at a time? And that would be something natural to try, right? So maybe the first idea you try is pick rules that generate more and more of X. Okay, for the time being, let's not even think about the time, how much time your algorithm is going to take. Just think of a procedure that is going to terminate and tell me whether or not the string is in the language. Okay, whether or not the string is generatable by the grammar. We'll then think about how many operations we're taking or other stuff. But can you even do it? What is one finite time procedure for doing that? Right. So for this, for this grammar, you might start by like drawing some diagrams. Right? S, I have two options. Either I can go to the rule 0A as 0, or I can go to just the terminal one. Okay, I'm just trying to explore all possibilities for now, right? And from here, I have three options because I can replace A and directly go to 0S0. I can replace S with 0A, 0S0. And then I get the other one is if I replace S with 1 directly. Okay. I mean, I'm just saying, if you give me the stats, the first thing I would do is kind of try and explore these possibilities, right? So even if you forget that, okay, maybe you're exploding the tree exponentially, there are other issues here. Yeah. That's a good question. I mean, this is just a very dummy example to kind of highlight the issues that might arise. And you're kind of pointing to some of the issues that we will get rid of. So, okay. So if you have something like this, what's in, so I would say you're not even, it's not just a question of, having an exponentially growing tree. It's much worse because you have branches that are kind of getting more complicated. They're not simplifying it, right? You started with S. Now you have like longer string, more variables. You have to explore those things. S is still there, so you haven't made any progress in any sense, right? So how would you handle this then? Any suggestions? Well, in some cases, you can make progress if you have some structure in the grammar, okay? And that structure that we will codify as a set of nice properties, okay? And the point of these properties is to make sure that when you apply a rule, kind of go down this recursion, you make some progress or simplify your task a little bit in generating or trying to find out if X is in the language. Okay, you don't want to say, okay, I'm going from S to SS, S to SS, S to SS, something like that. You're not making any progress towards your string X. Okay, those are the kinds of things that you want to avoid. Okay. And these properties, they actually have a very interesting history, especially coming from linguistics. As I said, as I briefly mentioned, context-free grammars were studied a lot in linguistics. And there it was an important question. If I have a grammar and I give you a string, how would you know that the string is actually part of the language of the grammar, right? And this leads to something called Chomsky-Normal form. All right. And these are some very seemingly rigid properties, but as we'll see, very helpful, at least in our task of deciding if a string is in the language or not. All right. And so a grammar G is in CNF format if it satisfies the following properties. And we'll see some examples anyway, but let me state them. Every rule is, by and large, except for one exception, all rules can only be of two types. Either the rule is of the form, some variable goes to two other variables. Okay, or you can have a variable go to a terminal. Okay, so you don't allow things like a goes to epsilon anymore. It has to go to like a terminal. If it's going to epsilon, what is the purpose of it, right? So we're kind of blanketly saying, okay, don't have such irrelevant rules. Okay, we'll only have meaningful rules in some sense, under non-redundant rules. That's what I want to say. Okay, so a variable goes to two other variables, or a variable goes to a terminal. You can't mix, at least under these rules, a variable and a terminal on the right hand side. Okay, you're putting a lot of structure on the kind of rules that you're allowed. Okay, in addition to this, you have two other minor constraints. I would say these are the main stuff, and then one exception. You can have a rule S to epsilon. Okay, the only way epsilon can appear is from the starting symbol. Again, this is just so that you can get the empty string in the language if it is necessary. Okay, that's the one thing. And the other rule, which I think is far less constraining, is that start symbol does not occur on the right-hand side. Okay, by and large, I think the fact that all rules look like A to BC and A to A, that's kind of much more constraining. These two are also there, but these are also helpful, but those two are really critical. Okay, is the definition clear? I'm just, okay, I said, okay, if all rules look like this, then some might want to say the grammar is in a nice form. It's in what's called a Chomsky-Normal form. Okay, yeah.
So for the first part of rule 1, it's strictly only two variables on the right-hand side.
Yeah.
No terminals, right?
Yeah, strictly only two variables on the right-hand side. They could be the same variables. It could be A to A is allowed, but you cannot have A to ABC. You cannot have A to A, and so on, where A is a literal offset. Let me give some examples, right? So you can't have something like A to ABA. This is not allowed. A to 0, 0, not allowed. A to B0, not allowed. Okay, none of these are allowed, but you can have something like A to A, that's fine. A to 1, that's fine. A to AB, that's fine. S to epsilon is fine, but you cannot have something like A to epsilon. That's also not fine. Okay, and also you can't have something like A to B. Again, you need to have at least two variables on the right hand side. Yeah,
Two or more?
Exactly two. Exactly two. Yeah. Oh, because one is a terminal. Yeah. Okay. Yeah.
So why is A to empty string?
I mean, again, it's kind of not necessary, basically, as we will see. Okay, so the only where epsilon can be part of the grammar is from the starting state. S to epsilon is allowed, but for any other variable, it's not allowed. Okay, yeah.
Will this form allow us to avoid the pitfalls you described a little bit before it?
Much, yeah, very easily, actually, as we will see. Like, you immediately start making progress. Okay. So I should say A to 0, that's also allowed. You can have any terminal on the right hand side, that's fine. Okay. So the point is, like, when you have this structure, essentially, once you introduce a variable, it has to go to a terminal. So it kind of makes some progress. Like you can't have like, after some point, you only have to look at strings of certain length. Okay. All right. Well, we'll talk about why, assuming that the grammar is in CNF is reasonable in a bit. But let's see, is this helpful? Like, why would such a form be helpful first? Yeah.
Is everything that is expressible without this form also functionally expressible in this form?
Yes, we will get to that. Okay. But let's, even before that, let's see if it is useful, to have this format. Okay. Or, maybe let's just state it. We will see the proof of it in a second, but I want to do it in a slightly different order. So the first theorem we'll show is that for every grammar G, there is another grammar GCNF, okay, such that the languages generated by these two grammars are exactly the same. Okay, essentially, you give me a badly written grammar, I can get rid of all the redundancies on it, so that you end up with a grammar somehow which is much nicer to work with. Okay, and this nicer is the CNF form, and once you have it, as we'll see, we can do a lot of nice stuff. Okay, such that for all x, the function computed by the original grammar is exactly the same as the new grammar that you write down. Such that GCNF is in CNF and satisfies. Okay. This is called Chomsky-Normal form because this was introduced by Noam Chomsky back in, I think, 60s, if I'm not wrong. Okay. So this is something we will show. It's kind of, a little bit tedious to show you. You have to do a bunch of case analysis, but we will kind of do it a little bit. But the more interesting thing, I think, is that if G is in CNF, then we can compute okay. So if you give me a grammar in CNF form, then it is not too hard to compute. If I give you a grammar in CNF form and I give you a string X, you ask me, okay, is this string X in the language? Then we can do it with some few lines of recursive code. Okay. Without CNF, it's messier. So what you would do then is this algorithm, the part of theorem 1, that also we do it by an we'll give a procedure kind of which takes one grammar as input, converts it to CNF form, right? You don't have to do it manually every time. Okay, there is an algorithmic way to do it. And then you combine it with the second algorithm. It says that once you have something in CNF form, you can check whether a string is in the language or not. Okay, all right. So let me talk about theorem 2 first, and because I think it's shorter, cleaner, very elegant, right? So proof, or let's say how to compute fg of x if g is in CNF. Okay, and again, don't worry too much about time complexity. You can make this pretty efficient, but for now, let's just focus on whether or not you can even compute it. Okay. So any suggestions? So the basic thing that you want to exploit, given the grammar is in CNF form, is if I introduce a variable, okay, then it is going to go to a literal. You cannot get rid of it. Like, if I introduce a variable, then I have to introduce a literal for it, introduce a terminal for it. Okay, so I only have to look at strings of certain length. Beyond that, if I have to go beyond that, then you can just get rid of it. Okay, Like you don't have situations like, okay, I went all the way to 0, A, 0, A, 0, but then I can get rid of A and then it kind of shrinks, right? The shrinking can never happen, okay? So that's the main idea, but the way you would write it is you can write some simple recursive code, okay? So let's say the grammar G is V sigma R S, right? And what we are looking for is I want to go from S to something, and so on, and we have X, okay? So recall our input is the grammar and a string X, which is part of the terminals. All right. And okay, so the brute force way to do it, as I said, you can also do it much more efficiently, but let's not worry about for the time being. So if I start from S, right? Okay, there is the S to epsilon that only is necessary if your X is the empty string. If it's not, then that rule is irrelevant. So the rule that you apply is either you directly go to a terminal, okay, which you would check if X is a single terminal, but if X is longer, the only thing you can do is check, you have to go to 2 variables. Okay, so some 2 variables. And you go to something like S goes to maybe say A and B. Okay. And once I go here, this is going to generate some string. B is going to generate some string. Right? And we want basically, we want to check, is there a way to go from S to some 2 variables A and B so that A generates like a portion of X and B generates whatever is left, right? Almost brute force. I'm just saying, okay, go through all A and B, check if A can generate the first half and B the remaining. A can generate, maybe the first 1/3 and B the remaining, and so on, right? And a clean way to do that is to define a recursive program, and then you can make it efficient by some sort of dynamic programming. So for every variable A and a string Y, let's define check AV is Y generatable from A. Okay. In other words, you're asking, if you start from A, it need not just be the start symbol, any other variable. Can I apply the rules of G and end up with this terminal sequence? Okay, suppose I'm just defining this function, and I'm going to write down some recursive code for computing it. Okay, so if the length of Y is actually 1, if Y is a single terminal, what should you do? When would you return 1? When is Y derivable from A? Like, there's only one option, right? If A to Y is a rule, like it has to actually be the rule itself. Like there's no other way, right? Return 1, else return 0. Okay. And if length of Y is greater than or equal to 2, then what would you do? Well, I can say for every rule A to B, C, for every split of Y as Y1 and Y2, Okay, they don't have to be equal, but they have to be not empty. Okay, so I consider all possible splits, like the first symbol of y goes into y1 and everything else goes into y2. The first two symbols go into y1, everything else goes into y2 and so on. Okay. Say if check of b comma y1 and check of b comma, well, if both of them are okay, if both of them are 1, then you return 1. All right. And otherwise, here you return C. Yeah. Oh, sorry, it should be C. Thanks. That would be a blunt. That would be a pretty bad program. Thanks. And having it in CNF form really helps because that's what allows you to. So you're making some progress now because the lengths of y1 and y2 are shorter than the string you started with. Like if you're writing a recursive program, you have to make some progress. Otherwise, you might just keep looping forever. Okay. And here the loop is in the progress is in the length of strings that you're looking at. I'm looking at a string of length n. In every recursive call, I'm looking at strings of length at most n minus 1. Okay. Yeah. Yeah, but there's only one rule that can go to the empty string, s to epsilon. Yeah. So, I mean, here you would say like, unless y is epsilon to begin with, right at the beginning, you don't have to think about it again. Okay. And, it's kind of, so that's why we also have this. A start symbol does not occur on the right-hand side. Okay. Any questions about this program? Kind of a simple brute force way, but as I said, you can make it efficient, use some dynamic programming, other tricks to make it work better. But that's not the focus here. So let's not dig into that. Okay. At the very least, we know that the context-free grammar function is computable if you are already in CNF form. If not, if I run the same algorithm and your grammar is not in CNF form, you will not find the answer. You might just get stuck in a loop. Okay. All right. So this kind of gives us half of the answer. The other half is how do we know that every grammar can be converted to something in a CNF form? So converting grammars. Okay, and this is, the way you do it is essentially you look at all possible violations of the form, of the Chomsky-Normal form thing, and then kind of fix them one after the other. Okay, sometimes you might have to redo the fixes because maybe you undid some other fix, but basically you go through each thing and then fix it. Okay, so let's think of various ways in which you can violate the Chomsky-Normal form. Okay, so one thing is you say maybe some easier fixes are, if a grammar for it to be in Chomsky-Normal form, the start symbol should not be on the right-hand side of any rules. Okay, that's number one. One of the rules. The other one is we cannot have variables and terminals mixed up. Okay, either you only have rules which have variables, or you have like a variable going to a terminal, but you can't have like A goes to a terminal and a variable. Okay. No rules. Every rule must have at least, well, no rules of the form A to B. These are definitely not allowed. No rules, lots of rules. I can't have 3 or more variables on the right hand side. Okay. And the same thing for terminals, right? No rules of the form. Okay, I can't have more than 2 terminals on the side, right? And also you have no rules. Okay, so all of these are there. Okay. So, let's do like a quick sort of laundry list sort of check of fixing each of these things. Think of all of these as problems in our grammar, and we are going to take a hammer and fix each of these nails. Okay. So let's say the first one is this guy. We are not allowed to have a start symbol on the right hand side. What is one way? If I give you a grammar which has this, how can I transform it into a grammar which satisfies that start symbol is not on the right hand side? Any suggestions? Any suggestions? Yeah, I can just create a new start variable. Easiest of fixes. S1 and say S1 to S. Okay, so now S1 is a new variable, so it never occurs in anything else. And it's it's the same grammar, because the only thing you can do with it is just essentially go back to the old grammar start state. Okay. And the other one is we cannot have variables and terminals mixed up. Okay, so we cannot have rules of the form A goes to maybe B and 0. So this is not allowed. How would I transform this? Any suggestions? I cannot have something like B0. Yeah. But you can't have a variable to a variable. So that might work, but there might also be a simpler way. Yeah. Yeah, I think that's a easier fix. You can also probably make the other session work, but I think that's a cleaner fix. So you add a, let's say, new variable, let's say, for each terminal. Okay, if you had a terminal A, then you'll add a new variable. Let's just call it VA. And you just basically say, add new rule, VA goes to A for each terminal. Okay. And then in every rule, replace terminals. In every problematic rule, I should say. With corresponding variable. Okay. So if I had something like A goes to, maybe B and 0, then this whole thing will be replaced with A goes to B, V0. And I also have the rule V0 to A, to 0, sorry. Okay. Yeah. You mean here? Oh, here, because the only thing we wanted there was that the start state should not be on the right-hand side. So the start symbol should not be on the right-hand side of any rule. So we are creating a new variable S1. And then we said, okay, S1 goes to S. S1 is the new starting variable.
You can have the form. I thought it had to go from A to B.
Oh, okay, good point, good point. So we're trying to fix one at a time. Okay, so we'll fix all of these rules in one go again. Okay, that's definitely a very good question. Like, okay, I added this S1 to S, but it violates another property that we want in the end, which is no rules of this form. Okay, but we'll see how to fix those in a second. Okay, it's a good point. So yeah, so when we fix one problem, we might create more problems kind of lower down, but then you reiterate these things and then everything will be fine. Okay, it's a very good question. So how do I fix rules of the form A to B, right? I can't have things like A to B or S1 to S. These are kind of, almost seems like very redundant. So how do I fix that? Yeah. You do them in some order, it helps a little bit, but sometimes you still run into issue, especially with rule number 5. Think, when you do the substitution, you might go back, as we'll see, but then you do it again and you always reduce the number of violating rules. Okay, so you make progress. Okay, that's a good point too. I think apart from 5, you might be okay, but yeah, 5 is a little bit of a delicate. Okay, so how do I fix things problematic? If I have something like A to B, it's not allowed. How do I do that? Yeah. Exactly, right? If you have A to B, what is that rule really doing, right? It's just calling something else. So replace A to B as follows. Okay, so for every rule of the form B goes to blah, add rule A goes to blah. Okay, so just get rid of the rule A to B and you add new things. So for instance, let me maybe put this in different color. So for example, suppose I had S2, 0, S1 and epsilon. Okay, this was a grammar that we saw earlier, right? If I did the fix 0, then I would end up with S1 goes to S and then S goes to 0, S1. Okay, now I do fix 1, I'll do S1 to S, S to V0, S1, V1, epsilon, and then V0 to 0, V1 to 1. Okay, and then if I fix 2, what would I have? I would create, right? I'm going to just completely get rid of this rule and take C where S goes to and just replace them with that. Okay, this still has problems, but we'll fix them in a little bit again. This should be S. Sorry. Okay, any questions about this? Okay, so we got rid of some of the fixes. There's still quite a few to go. I mean, just 3 more, I guess. But so let's see. So the main things that we haven't fixed now are like, I have 3 variables on the right hand side, which again is not allowed, right? So to fix 3, which is no rules, like I can't have A2, A1, A2, A3, and so on. Okay, this is not allowed. So how can I fix this? Any suggestions? Yeah.
Just chain them up, kind of like what the curry does.
We have to chain them up, exactly, right? So if I have something like A2, A1, A2, A3 up to AK, then what I can do is essentially like create new variable for each intermediate thing. Okay. I mean, this is actually somehow what really happens in programming language anyway, but we can make it very explicit, right? So create new variables, and for each rule you have to get a new set of variables here. You don't want to confuse them across the rules. Okay, so for each create new variables, specific for this rule. Okay, you create new variables, maybe v1, let me not use v, let me call them w1, w2 to wk minus 1. Okay, and then you say I'm going to replace this a1 through ak completely with a goes to aw1, w1 goes to a2 w2, w2 goes to a3 w3, and so on. I'm just breaking them up, right? And okay, does this make sense? I created more rules, but it's a trade-off, right? You're reducing the length of the rule on the right-hand side, but you're creating more rules. I would say you're not losing much in the complexity. You're just looking at it in a different way. Okay. And so how about fixing 4, which is I can't have things like a goes to, even a string of literals. I can only have a single terminal on the right-hand side. This is not allowed, right? How can I fix that? Yeah. Yeah, so we can chain them up again exactly like we're doing here, right? So I'll say something like, okay, yeah, if I have a1, a2, and ak, you create new variables. Let me say maybe t1, t2 up to tk minus 1, right? And like instead of saying a goes to a1, a2 up to ak, you will say a goes to va1 t1, t1 goes to va2 t2. I guess here it should be yeah. Okay, I mean, kind of almost the same thing as we did earlier, but now you have this terminal variables that we created already, for each terminal. Okay. All right. So individually fixing each rule, I don't think is very complicated, but you have to do all of them one after the other, and then sometimes maybe you will go back, as we'll see. Okay. So now we have one more problem that we haven't talked about fixing, which is for that no rules of the form a to epsilon. So how do I fix this? Any suggestions? Yeah.
I mean, if that's like the only terminal A resolves to, then you can just get rid of A from like the full grammar or
But A could also go to other useful rules as well, right? But I think you can use the same idea. Just use it for each specific rule. Okay. So what do I mean? So if A goes to epsilon is something, then what I'll do is drop this rule, and for every rule with A on the right hand side, create new rules without it. Okay, so meaning suppose I had something like A to epsilon, and then there was some other variable, let's say B, which was going to, maybe CA. Okay, so what would these two go to? I would drop A to epsilon, but then I would say B to CA and just to C. Okay, so A could go to epsilon. So let me substitute that epsilon and I can drop that A to epsilon. And I had to do this for every rule whenever there was A on the right hand side. Just create a new copy of that rule without that A. All right. Now you can see there's some issue with it, right? Even if I was kind of close to being done in that every rule had at least two variables, I undid some of that progress because I removed the A. So now I have a rule B to C. Okay, so I have to go back and fix the problem that arose again. Okay, so you can actually minimize the number of fixings by doing these things in a specific order, as was suggested, but you can also just keep doing them until there's nothing else to fix. Okay, so so the procedure is keep applying the fixes until nothing is left to fix. Okay, so this is a lot like a lot of holes. You keep plugging some of them, and then while you're plugging them, something else opens up, but then you plug it again. But you make some progress because you're getting rid of some of the problematic rules. Okay. Any questions? Yeah.
For fix number 2, are we removing the old rule?
Yeah, we are replacing it, like getting rid of A to B and adding these things.
In that case, when we have the issue with the start state, those two rules like fix 0, fix 2.
They don't, I mean, it's not that they conflict, but you're doing 0 once, like 0 you only do once. And you did it first time, and then you go through the process as usual. It's not conflicting, but like it creates a problem for fix 2, but then you fix 2 and then you would be fine.
Okay, so if you go down to right here,
Mhm.
where we have fix 2 is applied to S1 to that rule and then S to that rule. So would we get rid of one of those?
Yeah, actually, yes. So maybe let's take this example a bit further and see what happens, right? This was where we ended up. We go down here, then what happens, right? So far, things are looking okay. And, I have like duplicate rules here, but that's okay, right? So I have to fix 3 because, I have these 3 variables here, right? 3 variables.
Well, then in the one below, you also have, oh, it's not the start variable.
It's not the start variable anymore. Okay. So what will I do? I'll say, replace this with S1 goes to something like V0, let's say this is rule 1, rule 2. So I have to create new variables, right? We said, okay, I'm going to create new variables, which are like W11, right? And then I'll say W11 goes to SV1, right? And that's just to fix the rule S1 going to V0 SV1, but I also have to do it for the next one. So I get S goes to V0, W21, 7. W21 goes to SV1. Okay. And I'm kind of okay with, I have fixed most things, but I still have this epsilon rule, right? S1 to epsilon is fine because the start symbol going to epsilon is allowed, but S to epsilon is not allowed, right? So if that's the case, then you have to do fix 5. If I fix 5, I will get S1 going to V0 W11 to epsilon. I'll get W11 going to SV1 and just directly to V1, right? Because this is a rule. There is a rule saying S to epsilon, so I'll create a new rule where S is substituted. Okay, then I'll do V0 W21 to epsilon. W21 goes to SV1 and directly to V1. Okay, now there's an issue that I created this rule which is W11 directly going to V1, which is not allowed, right? So I refix that. Okay, so fix 1 again. Was it 1? What was the number? Yeah, 1. Sorry, fix 2.
So the order of the rules is arbitrary.
You can do it arbitrarily, but I think actually if you do 5 first and then 0 then and 1, 2, 3, you're in better shape. Okay, but you have to do the starting thing first also. So the order of the rules is not that important as long as you keep making progress and you can show that this actually does progress. Yeah.
So the line S equals V0 W21 should be 4 epsilon. I want to be this.
Oh yeah, it should not be there. We just got rid of it. That was the whole point. Yes. Right. So we got rid of it. Okay. Now I have to fix 2. So I will say, I'll do, maybe I can. So it'll be S1 to V0 W11 epsilon, W11 going to SV1. And I have to replace W11 going to V1. So I'll just say this goes to 1. Okay, so now I have a grammar which is in CNF form. Okay, I think it is, otherwise you might have to do some more things, but I think it already is in CNF form. Okay, so there is a very mechanical procedure that you can do. And in fact, most parsers, that are implemented do have the such converters and even stronger, things, properties you can ensure for making it easy to check if a string is in the grammar. Okay, any questions about this? Okay, yeah.
Can you explain how the fix 2 works again, particularly? I think for like step 3, you had like S1 to S and then S to like B not S1 to 1. Like, yeah, right.
Yeah. So basically the way it works, if there is a rule which says A to B, okay, I'll get rid of the rule A to B and I'll add in rules which wherever B was going to, I'll just put them kind of after A. So like for instance here, there was S1 to S and S was going to these things. Okay, so imagine I did this and I did this. right? So we say, okay, let's shortcut this thing and add in the rules S1 going to all the places that S could have gone.
So it's kind of just like substituting.
Exactly, it's just substituting one step ahead. Okay, any other questions? All right, so I mean, that's those are the main things I wanted to say about CNF and grammar. The summary is that every grammar can be converted to CNF. That's number one. The other thing is we can compute FG of X. Okay. Given any grammar and a string X, I can compute FG of X. Okay. All right, so they are definitely not more powerful than Turing machines. That's no surprise, but we also know explicitly how to do this. Okay, so now let's take a 5-minute break. And when we come back, we'll start asking more meta questions about properties of grammars. Okay. Yeah.
Do you know where the exam solutions are?
They should be on Edstand, Darren.
I couldn't find them on the.
Okay, maybe I didn't make it public. I'll maybe it's in private settings. I'll fix it.
Yes.
Sure. Yeah.
I assume where we're going is that because context-free grammars don't suffer from things like the halting problem, so that we can reason about them in a way that we can't
Yeah.
reason about traditions.
At least some things.
Yeah, more things than we can know.
Exactly.
Yeah, please.
Wow, that's pretty.
Oh, whoa.
Are you guys taking feedback or not? I think it's kind of early to do that.
Well, we're meeting with everyone.
Yeah, I was gonna say it's kind of weird to have like the constant part. Like, you know, login, right?
I like the design. To be honest, I don't know, like this book, like how about the example to the lower side of external service screens. I think I said if I can find this. I think it's not. I don't know the problem with it. Then it's like
So FGFX just basically says whether the input string complies with the current object.
Yeah,
that's all. Just for clarification, I was not here for the first time.
Yeah.
Is that what I missed? Just like the beginning of this.
I think so. I mean, basically the statement that we were shooting for, like, you know, it's just checking whether X is in the language or
Right. And those languages are defined by rules. grammar is specifically rules, right?
Grammar is,
The set of rules, right?
yeah, and the variables and terminals.
Right.
Mhm.
Yeah, a little technical. Yeah. Still using
Professor,
Yeah.
how come we can't just get rid of this rule and just put W11 for W21 here?
We could, but in this case we could.
Yeah.
But in general, you don't want to conflate the variables just to make it very clear.
Okay.
In this case, it's not having an effect, so you can simplify it further. But
Okay.
there could be scenarios where if you mix these variables up, you might run into problems.
I see. Okay. Thank you.
All right, so let's get started again. Yeah.
Wait, pause. This is it's cool. That's so good. So doesn't nail out.
Okay, let's get started again. So there are a couple of questions, good questions in the break. One is that, so we replace the S to epsilon, do this fix 5 only for non-start variables. Remember, start to epsilon is allowed, okay? But that's okay because the start never appears on the right-hand side, so that's why we do that fix first. And the other thing is, like if you look at this instance, we could have potentially, this is W21 and W11 are doing the same thing, right? So you could save a little bit by bridging them together, but it's always better to use different variables each time. Okay. All right. So let's now ask some questions that we were really keen on answering for programs, right? So we were talking about programs. We wanted to reason about programs. That was unfortunately unreasonable. We could not because of Rice's theorem. Let's ask something about something similar for grammars. Okay, so what are some semantic, just as we define semantic properties of Turing machines, we can also define semantic properties of grammars, right? So we'll say, okay, I have a function On strings, again, we'll use strings as representing grammars. I'm not even going to elaborate on that. We've done it many times. Take any favorite encoding, you can just, whatever works, right? Just need to know that there exists such a thing. Okay, so we have a function that takes a grammar as input. Is semantic. Okay, in the same way that we define semantic properties of programs, it's semantic if it only depends on the language generated by the grammar. It doesn't depend on the exact rules you have, exact variables you have, the order of the rules, or nothing like that. It only depends on the actual function or language computed by the grammar, right? Semantic if for all grammars that are equivalent, meaning, let's say the grammar for LG for G is the same as the grammar for G prime, then you must have G satisfies the property if and only if G prime satisfies the property. Okay, so we are viewing grammars as binary strings, and under this thing, we can define semantic properties of grammars, right? It's a function of semantic if it only depends on the language generated by the grammar. Okay, so we can ask, for programs, any non-trivial semantic property was uncomputable. Okay, like really, really disappointing result. But fortunately, for grammars, something nice happens. Okay, at least some interesting semantic properties become computable now, right? We restricted the model kind of in its power in some way. And because of that, we are able to reason about the model now. Okay, you restrict the model, you restrict the programs that you can write, then you get better ability to reason about the programs. Okay, so let's take a very specific example, and I'll call this not empty CFG Okay, so not empty CFG of a grammar is one, if the language generated by the grammar is not empty. There is some string in the language. You can have silly grammars or seemingly, okay, they could look nice. So, I might have a grammar something like this. S goes to AB, B goes to CD, and A goes to 1, C goes to 0. Okay, so what's the language of this grammar? It's empty, because once you start from S, you will end up with the variable D, and there's nothing that lets you get rid of the variable D. Okay, so there is no string in this language. So LG is actually the empty set. Okay, now we're asking, okay, is there a procedure which can take this grammar as input and immediately tell me, okay, this grammar is empty. The language generated by this grammar is empty. For Turing machines, of course, we saw that this is uncomputable, but for grammars, it is computable. Okay, so just as an illustration of the utility of grammars, we can ask, not empty CFG is computable. Okay, and as I said, the main takeaway should be that restricting power of models allows us to reason about them. Okay. All right, but how do I, how can I check if I give you a set of rules? What is one way to check if there is a string that is generatable from this? Is the language empty or not? Any suggestions? Yeah.
At least in the case of that, it only occurs when there's no terminal for something. How it's called there.
Okay, so that's kind of a good starting point. So the idea is kind of, says so kind of start tracking backwards, right? You'll say, okay, terminals are good. If I can reach something with only terminal, that's what we're shooting for, right? So the start by calling variables that reach only terminals good. Okay, if I have a rule like a to 0, a is a very good variable, right? If I get something with only with a's, I can just get rid of it. Okay, what else can I do? What's the next step up from this? Yeah,
Variables that go to those variables are also good.
exactly. Like if a variable only goes to good variable, if there's a rule which says, okay, b goes to a, then b is also good now, right? Because a was good, I could get rid of a and get to terminals, so b also is fine. Okay, so that's the first step. And now you would say, variables that go to only good variables with a rule only good variables on the right. Are also good. Okay, and that's it basically, right? And when would the entire grammar be good or not have a not empty thing? Well, the start variable is good. Okay, so if start is good, we are all good. Then LG is not empty. Okay, so if I were to write it as an algorithm, maybe I'll take a slightly bigger box and say, okay, so okay, you maybe say mark all terminals as good. Okay. And while any changes are made, typically you would do this by like having some flag. You say if a variable a has a rule that only has good things on the right, mark a as good. Okay, you keep doing this until you stop making any changes. Yeah. Yeah, as if it has only one rule, that's enough. Because if it has one rule, then there is some way for me to get rid of it. Okay, and that's all we care about. Okay, whether or not I can get rid of that variable. Okay. And in the end, you say if start is marked good, you return 1. Else, okay. Any questions? All right. So some properties, some semantic properties of grammars are at least computable. Okay. But you can't expect that, I mean, we can't be too optimistic and hope something like an anti-Rice theorem saying every semantic property is computable. That's not possible. And this is not something that we're going to prove. It's kind of quite technical to prove, but you can show that there is a weird thing about grammars, and we'll touch upon that in a little bit in the homework actually, is if I consider the following, I'll call it is full. Is full of a grammar is 1 if the language of the grammar is the entire string, like is sigma star 0 else. Okay. So the grammar is, is full if every string is part of the grammar. Okay, it's kind of a very trivial grammar as well, right? You can generate any string in that grammar. There is no restrictions at this point. Okay. And for instance, I can have something like, let's say, S goes to 1S, 0S, and epsilon. Okay, so this is a full grammar. It generates every possible string in 0 ones. Okay. And something that we're not going to prove is that is full is uncomputable. Let me put double exclamation mark in this. Okay. We are not going to prove this. I find this very surprising that, something close to is full, not empty, is computable, but kind of the opposite, it's not computable. We are not. I can check if the grammar generates at least 1 not empty string, but if whether or not it's kind of trivial in the sense that it has every possible string, that I cannot check. Okay, so some semantic properties are computable, some are not. So in some sense, the space of grammars, reasoning about them is a lot more interesting than reasoning about general Turing machines. Like there's no one size fits all answer, right? There are some things which are computable, some things which aren't. And then depending on your task, you have to come up with algorithms or understand why you cannot have that. Okay. Any questions about this? Yeah.
For non-empty, is there any restriction on the grammar like being in CNF?
No, it doesn't have to be.
Then how do we guarantee that the while loop doesn't include?
Well, if we stop making any changes, then we break out of the loop. That's what I meant by any changes are made. If I don't mark a new variable as good, then I stop. Okay. All right. Yeah. That's an excellent question. It is equivalent to computing empty of not G. But there's a catch there. Grammars are not closed under complement. The negation of the language of a grammar is not context-free. Okay, that's kind of again very confusing thing about grammars. We think of them as more powerful than DFAs and so on, but the complement of a grammar is not context-free. I mean, not always context-free. Yeah.
Is part of the reason this is uncomputable because the input set is infinite?
No, but you could have said the same thing for not empty, right? So I mean, between not empty and is full, from the look of it, both look very similar, right? And in fact, as was pointed out just now, is full of G almost looks like empty of not G. Like, let's say if there was a grammar computing the complement. Okay. But as I'll say later, there are grammars for which the complement is not context. Okay. Any questions? So towards that end, let me tell you about reasoning about limitations of grammars. We're talking about many things. We can compute grammars. They can generate very interesting languages. They are there everywhere in programming languages and so on. Amazingly useful across many fields. But at the same time, they are also substantially limited than general Turing machines. Okay. And I said, okay, they're more powerful than regular languages, but they're less powerful than Turing machines. Okay. And we'll see one way to show that certain things are not context-free, right? And this is limitations of CFG. Okay, so there is a version of pumping lemma for context-free grammars, which allows us to show limitations of grammars. Okay, if I give you certain languages and I ask you to, I'll give you a language, as we'll say, something seemingly simple enough, but there is no grammar that can generate. Okay, simple twist on like 0 to the n, 1 to the n, which we saw was context-free, that becomes not context-free. Okay, and the specific example I will use is the following. So claim, consider the language 1 to the n, 2 to the n. Okay, maybe I'll use. So the language 0 to the n, 1 to the n, we saw in last class that it is context-free, right? I can go to s to 0, s1, and that was fine. Okay, but if I put a new symbol, is not context-free. Okay, so as soon as I just add this one extra thing, it becomes not context-free. And the way to reason about this is very similar to the usual pumping lemma, with a small twist. Okay. So if you recall the pumping for DFAs, it was something like for every regular language, there was a number P such that something happened, right? And the same thing kind of structure holds for every grammar G, there exists a number P such that for all X in the language, if the size of X is more than P, then X can be written So for DFS, it was something like I can break up X into 3 pieces so that the middle piece could be pumped, right? And while still being in the language. For context-free grammars, it's not as simple, but I can break up the string into 5 pieces. Okay, I can write it as these 5 pieces such that one. So for DFAs, we said something like I can pump up the middle piece, right? There are only 3 pieces, so I could pump up the middle piece. For CFGs, it's, I think, very subtle as to why this happens, but the twist is that you have to pump the second and fourth pieces together. Okay, so they kind of are paired together. Okay, so all of these will be in the language. Okay, so there's some way to split it up into 5 pieces so that you can pair up the second and fourth piece, and they are always increasing in tandem. To increase them in tandem, you will be in the language. And then you have the other stuff like, B and D is not empty. One of those two is, at least one of those two is not empty. And the length of the piece, the middle piece is at most B. Okay, very analogous and similar to what we had for regular languages, but it's a bit more subtle. Okay, there's 5 pieces. It's not just that A to the B to the IC is in the language. I also get to increase. I also have to increase the number of times D appears. Okay. And we know that it can't just be the same old pumping lemma, because we saw things which are not regular, which are context free. Okay. So, we won't prove this statement here. Let's take it for granted and let's just see how to use it. Okay, using it is kind of, again, you have to come up with a challenge string and then show that there is no way to split it up into pieces so that you will always be within the language. Okay, so let's see one way to use it. So why are not grammars everything? It's because of things like this. So what might be a good challenge string? Any suggestions? Like, we saw something similar for DFA. So the argument here is fairly along the same lines. Like, you have to come with a challenge string, show that it cannot split up and so on. Any suggestions? So suppose L was context free. Then there exists a number P such that something holds. What might be a good challenge string? Any suggestions? You don't have to overthink it. Let me say that. Yeah. Yeah. So let's take the challenge string, 0 to the P, 1 to the P, 2 to the P. Okay. So there is a string of zeros, the same length string of ones, and the same length string of twos. Okay. So if the grammar was context free, then you should be able to split it up into 5 pieces so that the conclusions of the lemma hold, right? And we can think of ways to split it up. We don't know exactly where the boundaries will be. But we do know something about this. The total length of BCD together is at most P. Okay. So in kind of DFS, we said, okay, the length of the middle piece, is the A and B together at most P. So it was easier to argue to say, okay, it's only 1, so it's only 0. So you can just, increase it in some way and so on. So here it's a little like, you had to have one extra step, that's all. Okay. So if this is the case, I want to say that there is no way to split up X as A, B, C, D, E so that, for all I, something happens. Why is that? Any suggestions? I want to say that no matter how you split it up, once I go to the second level, you cannot be in the language. Yeah.
You cannot create a substrate that is like less than or equal to PD that has all 3 digits.
Exactly, right. So because the length of these 3 things together is at most P. Okay. So it can straddle zeros and ones, or it can have ones and twos, but it cannot have all 3, right? Because it cannot cross the 2 things together, because then it would have to be of length more than. Okay. So this middle piece is of length at most P, right? You can imagine I have a tiny window of length at most P. No matter where I put it in the original string, can only have symbols of 2 types, either zeros and ones or ones and twos. It cannot have all 3. So as length of BCD is at most P, can only have 2 out of 0, 1, and 2. Okay. So either in fact, you can say that either it has only zeros and ones or only ones and twos. Okay. And why is that a problem? Well, that's a problem because now but then if I repeat B 2 times, I would have increased the counts of at least one of the symbols, but I would not have changed the count of at least one of the symbols. Okay. Then we'll have more of one kind. Okay. So either my BCD had only zeros and ones, in which case, when I increase them, I would increase the counts of zeros or ones, but not change 2, means I'm not in the language, right? Or the other way, if it has only ones and twos, I could increase ones and twos, but they're not changing zeros, so it would not be in the language. Okay. All right. Any questions? Okay, let's do one more example of the same kind of argument. Remember, we saw like palindromes was actually context free, like, when I have the same thing in reverse, but what is called double. If I have the same string repeated twice, then I end up with something which is not context free. There was a question, it can also have only 1 out of 0, 1, 2. It can have 2 actually. So it's from in chat. So here my BCD can really have like, can cover both zeros and ones. And you can't just say it has only 1. Okay. All right. because we're not putting any bound on the length of A and E. They can be anywhere, right? This middle piece can go anywhere. The only thing we know is that its total length is at most P. Okay. All right. For double, it's the same thing repeated twice. I'm just putting the semicolon in between to make it easier for me to prove it. Otherwise, you have to do some extra 2 cases. So let's maybe focus on the main idea. So let's have the semicolon. So it's 0, 1 star, comma, sigma. I mean, semicolon in the alphabet, but the strings that we're interested in is the same string W with the semicolon and then repeated. And I want to say this is not context free. So what might be a good challenge string? Any suggestions? Actually, the same string that would have worked for DFAs would also work here. So, okay. Any suggestions? Yeah? Yeah, that's it. This will work. Okay. So you write the string down, and I would say, it's after that, the argument is similar, but you kind of end up having to do one extra case usually. Okay. So let's say you start with the string. So I have a long thing. Geez. A sequence of zeros, a sequence of ones, a sequence of zeros, a sequence of ones. Right? Each of this is P things long. Okay. So now, well, if the language was context free, then you should be able to split it up into 5 pieces, right? You can have A here, maybe B here, and then C here, and then D here, and then E, something like this. But no matter what, the BCD is of length at most P. Okay, right? And you consider basically various cases, right? So I'll do one, and then you can tell me the others. Like, what if B, comma D are on opposite sides of the colon? Okay, if they're on opposite sides of the semicolon, like somehow imagine this BCD piece is right in the middle, C is the semicolon, B is here and D is there. What would be a problem? Yeah. Exactly, right? Because of the length constraints, each one is of length at most P. They will only have 1 or 0 in that case. So by condition 3, BCD is at most P implies P only increases 1, D only increases 0s, implies is not in the language, okay, which is a contradiction. And the other case is B and D are on the same side. What happens in this case? If they're on the same side, what's the problem? Yeah. Yeah, so that's it. Then after the semicolon, the length is shorter. So you're definitely not equal. Okay. So now A, B squared, C, D squared, E is longer on one side of the semicolon. Okay. And case 3 is kind of the silliest case of all, I think, is what if B or D contain the semicolon? Well, when I pump up, I'm ending up with more semicolons. I'm definitely not in language, right? If it contains a if B contains the semicolon, then when I pump up, I have more semicolons. Okay. So using the pumping lemma for context-free grammars is also similar. Like you have to think a little bit about coming up with the right Chapman string. And once you do that, you have to consider all possible ways of splitting it up and show that you get a contradiction to the pumping lemma. Okay, so the principles behind using it are similar. The proof is a bit more involved, but we are not skipping. We are skipping that proof. All right. Okay. Any questions about how we are using the pumping lemma here? All right. Okay, so if that's the case, let me quickly summarize some things. So summary of CFGs, right? First, they're practically very important. You know, as I said, in programming languages, linguistics, they're there everywhere, they're used everywhere. Whenever you try and come up with a new language, like a programming language, you first define it by coming with the grammar. Okay. They are more powerful than regular languages. Okay, and some semantic properties are computable. Okay, and there are also some annoying properties, I'd say. You know, something that you'll see in the homework is that CFGs are not closed under intersection. Okay, everything we saw so far was very good because, you know, everything was closed in an intersection. If I take the AND of two circles, it was computable. To DFAs, to regular functions, the AND was computable. Context-free grammars, that's no longer true. Okay, and you'll show this in the homework. Right? And so what we'll do next class is talk about other problems which are not just about programs that aren't computable. Okay, and I should say that the next 3 lectures are conceptually, I think, really groundbreaking, and you will never see more confusing set of 10 lines of code as we'll see in the next lecture. It takes a lot of effort to, you know, 10 lines, that's it, but it's very confusing. So be prepared. Okay, but we'll work through it slowly. Okay.